Hello, ladies and gents. We're going to do another torque problem. And this one involves a ladder. So here goes. A ladder that is 8 meters long is leaning against a smooth wall. The ladder weighs 200 newtons, and the coefficient of friction between the bottom of the ladder and the floor is 0.6. The ladder makes an angle of 50 degrees above the horizontal. How high can a person with a weight of 800 newtons climb up the ladder before the ladder actually slips? This is a torque problem. This is also an equilibrium problem. So we're going to start out with a sketch that's going to look like this. Here is my wall. Here is a side view of my ladder. And the ladder makes a 50-degree angle between the ladder and the floor. And let's begin by drawing all of the forces that are actually on this ladder. So let's take a look at this. In the middle of the ladder, there is going to be the force of gravity of the ladder. So the ladder's weight pushing down is going to be right there. Some unknown height on the ladder is going to be the force of the person. So I'm going to call this FP for force of the person. So what else is going on? The wall itself is pushing this way on the ladder, and so I'm going to call that the force of the wall. There is a normal force of gravity that is going to push upward on the bottom of the ladder, like so. And there is a coefficient of friction. So friction force is going to oppose motion. So let's take a look at what's going to happen. Which direction is the ladder going to tend to slip? Well, it's going to tend to slip that way. Because of that, friction opposes motion, so the force of friction will be in this direction. If we have a situation that is static, the sum of the forces in the x direction equals 0, the sum of the forces in the y direction equals 0, and the sum of the torques on the object equals 0. So we're going to begin with the x's and the y's, and then we'll do torques in a few moments. So to begin with, let's start with the sum of the forces in the x direction. So my sum of my forces in my x direction look like this. I have got the force of the wall is going to be equal to the force of friction. Those are the only two sideways or lateral forces. The sum of the forces in the y direction, I have one force up, normal force, and the normal force is going to be equal to the force of the ladder. This is actually the weight of the ladder, plus the weight of the person. And I'm just giving him different subscripts so I can keep ladder and person slightly separated. Now let's put our numbers in, and I'm going to start with y. My normal force is going to be equal to the weight of the ladder, and we're told that the ladder actually weighs 200 newtons, and the person who climbs the ladder is going to weigh 800 newtons. So the normal force upward by the floor is 1,000 newtons. Put a circle around that because that's kind of a nice thing to have. Okay, the force of the wall pushing it to the left is going to be equal to friction force. Well, you and I both know friction force is mu times normal force. So the force of the wall is going to be equal to mu, and we're told in the problem mu is 0.6 times the normal force, and we just found normal force over here. So normal force is 1,000 newtons. So the force of the wall will be 0.6 of 1,000 or 600 newtons. That's kind of nifty. So I've got force of the wall and I've got normal force. So I've got two criteria figured out. Now we're going to have to sum the torques. And in order to do that, I'm going to start with a clean picture because I want to make sure that we've got this very, very visible. Because the picture, I always figure, is the part that makes it easy or hard to visualize. So here is my floor and my wall. Here is my ladder. This is my 50-degree angle. And I want to sum the torques on the ladder. What is going to make this ladder twist or turn? Now, the pivot point I'm going to choose for my ladder is I'm going to choose my fulcrum or my pivot as the bottom of the ladder. And let's take a moment and draw all of the forces in. One more time. I've got force of friction this direction. I've got force normal that direction. Halfway up, I've got the force of the ladder. A little bit further up, I've got the force of the person. And then coming off the wall, I have the force of the wall. Now, I need to find the situation where the sum of the torques are going to be equal to 0. Now, these are torques on the ladder. And to do that, I need the component of each one of these forces that is perpendicular to, I only need the forces that are perpendicular to my lever arm, and my lever arm is my ladder. So I'm going to change colors, and I'm going to start drawing some little triangles. Since I am using this as my pivot down here, any force that goes through that axis of rotation will not cause a torque. So the nice thing about this is the normal force and the friction force mathematically will go away. So I do not have to worry about those two. So I only have 3 forces to worry about: ladder, person, and wall. So here goes. The force that is going to be perpendicular to the ladder is going to be this component right here. And if this is 50 degrees, this is going to be 50 degrees. So I'm going to just list my component forces. So the force of the ladder that is perpendicular is going to be the force of the ladder. This is going to be the adjacent side, so it's going to be times the cosine of 50 degrees. The force of my ladder was 200 newtons, times that cosine of 50, and I ended up with 129 newtons for that component. Now the force of the person, this is going to be the component of that force that is perpendicular to my ladder. So the force of the person, whoops, that's a big P, force of the person that is perpendicular to my ladder is going to be the force of the person, which I was told is 800 newtons. Again, this is the side that's adjacent to that 50-degree angle, times the cosine of 50 degrees. So the force of the person is going to be 514 newtons. I've got one more, and this is the force of the wall. So I want to find the force of the wall that happens to be perpendicular to my ladder. And if this is 50 degrees, this will be 40 degrees because this is a right triangle. So if that's 40, this is 50 degrees. I've got to make sure I get my picture right. And what's the component of the wall force that I want? Well, I want this bit right here. So in this case, this is not the adjacent side, this is the opposite. So my force perpendicular for the wall is going to be the force of the wall, which we found is 600 newtons. Where did we find that force of the wall? We found it just up here. Force of the wall is 600 newtons. And this is going to be the opposite side, so I'm going to use the sine of 50 degrees. And the force of the wall is going to end up being 460 newtons. Now I can sum my torques. So to sum my torques, the sum of my torques in, whoops, I wanted to change colors here. The sum of my torques that are clockwise are going to be equal to the sum of the torques that are counterclockwise. And here goes, because if this is my pivot, what is going to make the whole thing rotate clockwise? Well, that's going to be the ladder and the person. So clockwise is going to be 129 newtons, and this is halfway. The whole ladder is 8 meters. If the whole thing is 8 meters, where is the force acting for the ladder? Halfway, so that's going to be 4 meters. The other clockwise force making the whole system pivot in this direction is going to be the force of the person, which we found the perpendicular component is 514. And I don't know that lever arm L, and that's going to equal the one force making it rotate in the counterclockwise direction, which is going to be the force of the wall, 460 newtons. And what's the length of my ladder? 8 meters. So that's that lever arm. And when I do this, this ends up with 516 newton meters plus 514 newtons times unknown lever arm L. 460 times 8 is 3680 Newton meters. If I take 3680 Newton meters minus 516 Newton meters, and then divide the whole ball of wax by 514 newtons, I'm going to end up with a distance of 6.16 meters, which is how high the person can actually climb up the ladder before the whole system begins to spin. All right, see you later, folks.